All right, so chapter 10, which is energy. And last time we talked about a few things. We talked about really a couple type of processes. We talked about exothermic processes. And exothermic process is one where energy is released. And we also had endothermic, where energy is absorbed. We looked at some energy diagrams. And again, in those type of energy diagrams, when we look at our reactants going to our products, in this particular case, our reactants are higher in energy than our products. And that means that in order for those guys to kind of get down there, energy has to be released from the system. And that is an exothermic diagram. There's also that hill that the reactants has to climb to get to their side that we talked about, which is the activation energy. That again is the minimum amount of energy required for really our reactants to kind of get to the other side to our products to form those reaction. Remember, as in a chemical reaction, the only thing that's happening is we are breaking bonds. So as it sort of climbs up the hill, you got things breaking bonds. You also have things that are making bonds as well. To the very top, we talked about, which is the transition state. That is really the highest sort of energy state within the chemical reaction. There's also sort of a complex up there that is a partially made bonds, partially broken bonds as things are transitioning to their reactant or to the products, and then they will usually come down pretty quickly. The sort of endothermic version of this is very similar, except got something like this, reactants to products. In this case, our reactants are lower in energy than our products. That means energy has to actually go into here to allow this reaction to take place. It also has a greater activation energy hill that it has to climb to kind of get to the other side. One of the ways and very common ways that we basically represent energy in a reaction is the change in enthalpy that we talked about at the very end. Delta H is our change in enthalpy. And it's really kind of like the heat of a reaction. It basically tells you, how much energy is either sort of given off or absorbed in this particular process. One way that we very much represent either exothermic or endothermic processes is in an exothermic process, our delta H value is typically a negative value. And in a endothermic process, our delta H value is a positive value. One of the ways that we calculate it, we talked about at the very end, is we take the delta H of the reaction is equal to the delta H of all of our products minus the delta H of all our reactants. These again are values that you can look up in a table. They are sometimes referred to as the delta H of formation that you can find in a table. And we basically add up really all the energy of our products and we subtract from all the energy of our reactants. And that gives us a total kind of net difference in energy that occurred in this reaction. And the reason we do that is, as we also talked about, it is a state function. And state functions are only really two important things: where you start and where you end. And once again, in a chemical reaction, the reactants are your starting material, right? And really where you end, our ending material, is your products. So that's why, again, we take our products minus our reactants. Remember as well that we talked about at the very end that you do need to multiply the values you find in that table, for example, by the coefficients that are in the balanced equation to get the proper numbers. Any questions on any of that stuff there we talked about last time? All right, so I think we left off maybe an example here. So why don't you give this one a go? Let's calculate the delta H of this reaction. These, again, are table values that you could find in a table. So why don't you give it a go and see what you come up with and determine, is this reaction exothermic or endothermic? If this is pretty much all you're given is the sort of reaction or equation, and you're asked to calculate delta H for it, you basically need to go find a table. If it's not provided for you, it would be provided, obviously, for us. You will then again look up everything as we talked about. You want to make sure a couple of things when you do. You want to make sure that you do obviously find what you're looking for, but you also want to make sure you find it in the correct state as a solid, liquid, gas, and make sure you find the right value for that. So we're going to do our delta H of this reaction, which again is just our delta H of our products minus the delta H of our reactants. So here on our product side, we again do need to take the coefficient into account. So we got to take 2 times the value for the NaOH that we find in the table, minus 470 kilojoules per mole. Again, we're going to add it to our other one here. Coefficient is 1. The value for H2 is 0, which is very common for things that are in their natural state and not really combined with anything else. That pretty much takes care of all of our product side. We're then going to subtract it from our reactant side. We're going to do the same thing. We've got 2 times the value of sodium, which is 0 in this case. And we're going to add it to 2 times the value of water, which is minus 286 kilojoules per mole. So once again, this is the products, and that's our reactants. And if we do all that there, looks like we're going to end up with... We will end up with here minus 368 kilojoules. Again, what that tells us is the number is not really the important part here, per se. The sign is negative, and that tells us that this reaction overall is exothermic as energy is going to be released. Any questions on that calculation there? All right, let's try maybe another one. Let's give this one a go. Same thing, calculate delta H of this reaction. Take our products minus our reactants in this case. So let's add that up there. So again, taking the coefficient there, our delta H is going to be, we're going to take 16 times our CO value from the table, which is minus 110. Going to add it to 18 times our water value there from the table, 286. And once again, that's going to pretty much take care of all of our product side. We're not going to go to reactant side. Same deal. We're going to go 2 from the coefficient times the value there for our reactants. And we're going to add that there to 25 times 0, basically, for our O2, which is also from the table. And again, if we do that, we will end up with 16 times minus 110 plus 18 times minus 286. Then we're going to subtract that from basically 2 times minus 208 and give us a minus 6492 kilojoules. Once again, here, the negative symbol, our sign that we get for our energy, tells us this is an exothermic reaction, which is a combustion reaction. It does make sense. And energy is overall given off in this reaction. Any questions on how to calculate delta H? Yeah. Well, why did the... It should always be products minus reactants. I'm pretty sure I did on that last one, right? I hope so. Yeah, so we did, you always want to go products minus reactants on that. Yeah, yep. And that really has to go back to what we were talking about, the state function, the little graph with the guy, the hill guys who are hiking up the hills. And again, in these type of things, really the only important thing is kind of where you start and where you end. In a chemical reaction, really our ending spot is our products, the stuff on the right-hand side, and where we start is really the reactants, which is on the left-hand side there. Yeah. Other questions? Okay. I think we'll skip that one. It's very similar. All right. So the next sort of thing we're going to talk about is another way that we sometimes can really figure out the energy of a reaction and sort of what is happening. And this is specific heat. And these are not negatives or anything like that. So let's get rid of those signs there. The specific heat capacity is the amount of energy that's required to raise the temperature of a substance by 1 degree Celsius, 1 gram of it by 1 degree Celsius. And there is a specific heat sort of formula, and that is Q is equal to ms delta T. Q is heat, our energy, if you want to think about it that way. It has units of joules or calories typically. M is mass, and it has units of grams. Now, S here is the specific heat capacity. So let's go like down here. S is the specific heat capacity. It has units of joules per gram per degree Celsius. Are calories per gram per degree Celsius. These are the two common units of it. And that is, by the way, the definition of specific heat capacity is the amount of energy required to raise 1 gram of a substance by 1 degree Celsius. And lastly, our change in temperature is in degrees Celsius, is one of the few equations in chemistry that you actually do not change the temperature to Kelvin. You actually leave it in Celsius. And that's because our specific heat capacities are typically in Celsius. So it is really important. Also really important is the change in temperature, to make sure that you always do final minus initial. So it's always important to make sure that you do the final temperature minus the initial temperature when you do change in temperature. The specific heat capacity for liquid water is 4.184 joules per gram per degree Celsius, or 1 calorie per gram per degree Celsius. And clearly here, you need to know those numbers. Most of the time here, they really do use that kind of joules most of the time, but the calorie one does come up. That is, by the way, the specific heat capacity of liquid water. It does change if you're dealing with like ice, which is solid. It's more like 2. If you're dealing with like steam, which is the gas version of water, it's more like 2 joules per gram per degree Celsius. So it does change with the, the kind of different states. But liquid water, 4.184 joules per gram per degree Celsius. That number may look familiar to you. That's the number we saw earlier as the conversion between calories and joules. 1 calorie is 4.184 joules, right? So that is the conversion factor that we saw earlier on. Now, for specific heat capacity, personally, I do roll with S. Some books will roll with C, and some books will even write SH for specific heat capacity. So you might see some variable in terms of the letter that's used for it, but I would say S and C are very common sort of letters that are used for it. Now, same thing as when we talked about delta H in terms of if you calculate Q, and you end up with a negative value, that tells you overall this reaction is going to be exothermic. If you calculate Q and you end up with a positive value, it's going to be endothermic. And as we'll talk a little bit about later on in this chapter, if you calculate the specific heat, or Q in this case, at constant pressure, you are also calculating the delta H of the reaction. So it's a very similar way. Now, why is it important to always make sure for the temperature that you do it this way? It's important because if you look at this equation, the mass of your substance is going to be a positive number. The specific heat capacity is going to be a positive number. So the only way that you could end up with a negative Q is through the change in temperature. So you do want to make sure you do final minus initial, because that negative is important to identify whether or not this reaction is exothermic or endothermic. You just don't want to take the difference of the temperature. So if you do that, you'll get the same numerical value, but you may be incorrect in terms of is it positive or negative. So you want to make sure you do that. Remember, as we talked about, temperature is a relationship of sort of the energy being transferred. If somebody's temperature goes up, that means they gained energy, right? It's an endothermic process for them because their temperature is going to rise as a result of gaining that energy. Opposite is true if somebody's temperature decreases. That is an exothermic process for them because they release that energy. The result of that is we see their temperature start to come down. So, that's what you can kind of expect with their specific heat capacity. Also, the larger the specific heat capacity, the more energy is required to change the 1 gram of that substance by 1 degree Celsius. And the smaller the specific heat capacity, less energy is needed to see a bigger sort of temperature change in that 1 gram degree Celsius. That also goes back to sort of what we talked about a little bit earlier in terms of like the bathtub of water versus the coffee cup. Coffee cup, there's a lot less mass of water in there. So you could get that energy in there to raise the temperature a lot easier than a lot greater mass in the bathtub. It's going to take a lot more energy just to see that 1 degree difference in temperature change, as opposed to a coffee cup where there's not that much mass. So you can see a much bigger change in the energy. Here again, it's a table, and as I mentioned before, they do want you to obviously know this value. But as I mentioned before, as you can see, ice is 2.03 and steam is 2, so it does change with the state. Obviously here, these are lower specific heat capacity for these metals. All right, so once you want to try, determine the amount of energy as heat that is required to raise the temperature of 10-gram sample of aluminum. Has a specific heat capacity of 0.89 joules per gram per degree Celsius, and it's going from 25 to 58 degrees Celsius. Give your answer both in joules and calories, so give it a go. Look, so here we're looking to determine the energy. So we want to think about our specific heat equation. Q is equal to ms. That's great, that delta T. So we're actually looking for Q here, and this is a reminder that very often people will kind of get these two backwards. So Q should only have one unit, either joules or calories. And again, the specific heat capacity should have 3 units associated with it. We have the mass given to us as 10 grams. We have the specific heat capacity, which is 0.89 joules per gram per degree Celsius. So that's what I was talking about. This guy should always have 3 units kind of with it. So hopefully we won't get those backwards. We have an initial temperature here of 25 degrees Celsius. We've got a final temperature of 58 degrees Celsius. So we have everything we need, I think, here. We'll just pop it in. So Q is equal to 10 grams times our specific heat capacity, which is not that number, but we'll use the one in the problem. Again here. All right, so it's actually 0.89 joules per gram per degree Celsius. We got our final temperature, which is 58, minus our initial, which is 25. In terms of the units, the grams here are going to cancel. The Celsius is going to cancel. That will leave us joules, which is a unit of energy, and that's what we're looking for. Again, 1 unit left over. We'll multiply that maybe here. So 58 minus 25. 58 minus 25, there we go, times 0.89 and times 10. It's going to get us about 293.7 joules. Again, sig fig wise, when you do this subtraction, you're at 33, which is 2 sig figs, 2 sig figs, and 3 sig figs, which means technically speaking, sig fig wise, we're probably looking at something like 290 joules in this case. We do want to convert it also into calories. So again, 1 calorie is 4.184 joules. So we could take the rounded number or the other number. You'll get pretty close to the same number, I think. We can go 4.184 joules on the bottom, 1 calorie up on top. Again, those are going to cancel. And we'll go here. Looks like about 69 calories. If you did not use a rounded number, then about 70 calories, I think, is what you got on that rounding there, or that non-rounding. This also tells us when we look at the Q value here, it is a positive value. So this is a endothermic process that's occurring here again. And we see that as a result of the temperature did increase. So the only way it went from 25 degrees up to 58, it had to pick up some energy to basically do that. Any questions there on that one there? Okay. Let's try another one here. We got 294 joules of heat is transferred to 10-gram sample of silver at 25 degrees. What will be the final temperature of silver? Specific heat capacity of silver is 0.24 joules per gram per degree Celsius. So here we're looking for a final temperature. So let's give it a go. Okay, so let's take another look at this one here. Again, we'll go with our specific heat equation since that's obviously what we're dealing with. The This is 294 joules of heat. So again, Q is heat. So that's 294. Again, we have a mass of 10 grams. We also have an initial temperature here of 25 degrees. We are looking for the final temperature. And we're given the specific heat capacity there is 0.24 joules per gram per degree Celsius. So we do have this, this, and this. So we could use the information really to solve for the change in temperature. That does mean we need to take all these guys and divide it basically to the other side. And if we do that, that'll give us a change in temperature here is going to be Q divided by MS. Put it in our values there. That's a 294 joule. That is a 10 grams. And our specific heat capacity here is 0.24 joules per gram per degree Celsius. Joules are going to cancel, grams will cancel, degrees Celsius will flip to the top when you divide it. You're going to take 294 divided by 10, hit equals, divided by 0.24, hit equals. And that is going to give us a 122.5 degrees Celsius. The reminder is, though, that that is not the answer. That is actually the change in temperature, right? So we do need to find our initial. So that, again, is why it's important here. Our change in temperature is our final temperature minus our initial. So in this case, we have 122.5 degrees Celsius. I'm not going to use a rounded number, so I'm not so far off to probably what the true value is at this point, so I'm going to continue on. Temperature final minus our temperature initial. So this should hopefully show you that you actually need to add that right back to the other side and subtract. So if we add that 25, that's going to give us now our final temperature, 147.5 degrees Celsius. At this point, I could kind of go back maybe and clean up some sig figs and all that good stuff. So really based off of what we did up here, we have 3 sig figs, 3 sig figs, and 2 sig figs, which means technically speaking, this number should have ended up at 2 sig figs, which really would have been like a whole number, right? Something like 120. And that's important here because now we're subtracting. So that's basically a whole number minus a whole number, which means we really should end up at a whole number over here because we should be looking at decimal places at this point, and that would be 148 degrees Celsius would be our final temperature here. This also makes sense because it did absorb energy as it gained basically 294 joules of energy, which was positive. The result of that is we should see the temperature go up, right? So if we ended up with a lower temperature than what we started with, you're definitely going in the wrong direction because it absorbed energy, and that should reflect in the temperature as increasing. Any questions on that point there? So again, in a situation like this, where again, as I mentioned, this is not going to be really our final sort of answer. We're going to use it. I would kind of avoid rounding like I did there, just to probably put you closer to really the true value. Again, there's a pretty big difference. If you did use the rounded number like 120, you would end up like at, 145. So that's a whole 3-degree difference, pretty big difference between them. So again, you probably want to avoid that to the end. Any questions on that? So let's talk a little bit about another common thing that happens with specific heat capacity, and that is, again, the sort of transfer of energy from one object to the next. As we talked about, there's sort of an idea like a perfect energy transfer. If somebody loses a certain amount of energy, somebody else will pretty much gain that amount of energy, so there's this nice transfer of it. So for example, let's just say that we had a piece of metal here, and we have like a beaker or a cup of water over here. And let's just say initially here, the mass of the metal is, I don't know, we'll go 98 grams. And we heated this metal up to like 99 degrees Celsius, right? And over here, we got about, I don't know, we'll go 110 grams of water. And we'll say our water was initially 27 degrees Celsius. And if I take this piece of metal then and basically drop it into the water over here, which way should the energy transfer? Should the energy transfer from the metal to the water or the water to the metal in this case? Which way should it go? Heat travels from cold to hot or hot to cold? Travels, not everybody at once, please. So it travels from hot to cold. Yeah. So in this case, the hot piece of metal is going to transfer all that heat and energy right to our water, which is colder in this case. So in terms of the metal, this is a exothermic process, right? In terms of the water, it's an endothermic process going to pick up all that heat and energy. Now, what's going to happen to the temperature of the water is we should see it increase because we threw some metal in there, and we'll just call it went up to say 29.5 degrees Celsius. Now, from this process, if I throw a piece of metal into this water, eventually the metal should start to cool down, right? And since it's sitting in this cup of water, it should eventually cool down to the same temperature as the water, right? It's going to reach equilibrium with the water temperature. So by doing this, and we know the temperature of the water, we will also know the final temperature of the metal should be the same at 29.5 degrees in this case. Now, how can this help us? For example, let's just say we wanted to know for the metal, what is the specific heat capacity of the metal? So this is a very common sort of procedure that because we always know the specific heat capacity of liquid water is 4.184 joules per gram per degree Celsius, we oftentimes can follow what happens with water and relate it back to, for example, the metal in this case or something else. So for the water here, we have actually everything that we would need to figure out the amount of energy that the water gained. So let's do that. So if we do it for the water here to figure out how much energy it gained, the mass of the water here is 110 grams. The specific heat capacity of water, 4.184 joules per gram per degree Celsius. And our final temperature here, 29.5 minus 27 degrees Celsius. And here, 4.184 and times 110. So this is going to get us something with my made-up numbers of 1150.6 joules, as the grams will cancel, degrees Celsius will cancel, and we're left with joules. Now, again, significant figure-wise, the subtraction here is 2.5. That is 2 significant figures. That is 4 significant figures. And that is 4 significant figures. So really, our answer here should actually, again, be at 2 significant figures. Once again, we're going to avoid rounding because I'm going to use this number in the next calculation. But again, you want to kind of keep track of that along the way. Now, how is this going to help me get to the metal? I know that in this particular case, all the energy that was gained by the water came from one source, right? So all the energy that was gained by that water came from basically one source, and that was the metal. So there is a relationship that we could have between, say, like the metal in the water, or the object in the water is Q of the metal will equal negative Q of the water. And that is because it is endothermic for the water, but it should be exothermic for the metal. And that is what a negative value would be. So our Q of our metal in this case will be negative 1150.6 joules, or minus 1150.6 joules. So using that relationship, the sort of opposite relationship, we're now able to, by just following what happened with the water, figure out how much energy, in this case, that the metal actually released. Any questions on that there? Now, that's really helpful if we think about the metal now and our specific heat equation for the metal. If we look at Q for the metal is equal to ms delta T, we now have the energy from the metal that we just did. We have the mass of the metal. We have the change in temperature of the metal. So we can now solve for the specific heat capacity of the metal by taking both of these guys and dividing it to the other side. And that will give us our specific heat capacity of our metal will equal the Q of the metal divided by M delta T. So putting in our numbers, our Q of the metal minus 1150.6 joules, our mass of the metal 98 grams. And now it's really important here to again make sure that you do final temperature minus initial temperature for the metal. So for the metal, our final temperature is 29.5 minus our initial, which is 99.0. And that's important because when I do this subtraction, what type of number will I get? A positive or negative? You can get a negative. That negative with our negative up here will turn our specific heat capacity of our metal into a positive number, which is what it should be. So again, those negatives you got to be kind of careful of as you go through it. So again, I'm using the whole numbers, so don't get too much rounding errors. We're going to go divided by 98, divided by 29.5 minus 99. And let's see how bad I did here on my made up numbers. Not too bad, actually. So that's going to get us here 0.17. The units here do not cancel, so they all stay. And that's good because we need all three of those units. Joules per gram per degree Celsius would be the specific heat capacity of our metal. Now, you may be asking, how did I get to 2 at the end? And it is based on this calculation here. Our answer here should be 2. So when we came up here, this actually should be 2 significant figures. This is 3 significant figures. And when we do the subtraction of our temperature here, we actually get 3 significant figures, which means ultimately we should end up with 2 significant figures here on our final answer. And ultimately it was based on the first calculation that we did up there at top. Any questions on that? So that is a very, very common sort of specific heat process and a very easy way to figure out, how much energy is being released or absorbed in a reaction. Frankly, all you need is some water, a thermometer, and a couple of styrofoam coffee cups like you're going to do on Wednesday. And you can basically figure out how the heat is being transferred or absorbed in a chemical reaction. It also works really well, for example, even if you're not throwing a solid into the water, you could take 2 solutions and mix them together because they're pretty much water-based. You can still do the same type of calculation. So it's a very simple way to figure out how much heat and energy is either being absorbed or released in a particular reaction. Any questions on any of that there? All right, so there is this relationship, and again, when we have 2 objects that are equal transfer of energy, the overall heat should be 0. Now, this relationship is basically the Q of the water is equal to, or the Q of the metal, for example, is equal to minus Q of the water. The difference is when you take something to the other side, all these guys over here, they become negative. So you got to have that negative distribution. Otherwise, you will get the wrong answer. So you got to just make sure, if it equals 0, you can set these equal to each other because you basically could set Q of the water, which is ms delta T, all for the water here, and Q of the metal, which is equal to m of the metal, s of the metal, and delta T of the metal. Because these guys are equal to each other numerically, you could set both of these guys equal to each other, but there is a negative that does need to be distributed when you do that, and that's what's up here. Basically, you got to make sure you do that. All right, so why don't you try one here? We have a 110 gram sample of a metal at 55.5 degrees Celsius. Raises the temperature of 150 milliliters of water from 23 to 25.5. Where you're looking for what is the specific heat capacity of the metal. So give it a go, see what you come up with. Okay, so let's take a look at this. This is very similar, obviously, to what we were just talking about. So we have a metal, and it does have a mass of 110 grams. It has an initial temperature here of 55.5 degrees Celsius. It raises the temperature of some water, so we got some water happening. And we have 150 milliliters of water, and it has an initial temperature of 23 degrees Celsius. It raises to 25.5 degrees Celsius once we kind of throw the water in, or the metal into the water. In this particular case, we are looking for the specific heat capacity of our metal. We do know just based on the temperature difference, our metal here again is a hotter temperature or a higher temperature than the water initially. So when the metal goes in, it should release the energy into the water. So again, here it should be exothermic for our metal, should be endothermic for our water. We see that in our water because our temperature of our water has increased. We also know from our conversation a second ago that the final temperature of that metal is eventually going to come to the final temperature of the water. So we do know the final temperature of our water, or sorry, metal is going to be the same here as our water in this particular case. So just like before, we pretty much have all the information for water because we always have the specific heat capacity of liquid water, 4.184 joules per gram per degree Celsius. So again, in this case, what we're going to do is basically figure out how much energy was absorbed by the water. And we know that that has to be the exact amount of energy that was released by the metal, as that is the only thing that's going to cause the change in our water's temperature. So our specific heat capacity here for our metal, not metal, sorry, try again. Our specific heat equation for our water is going to be ms delta T. We don't have the mass given to us. This is actually the volume. So we do need to convert our volume into mass so all the units cancel out correctly. Remember, in a situation like this, density would be the one that you're looking for. Since you have volume, you have density. Mass would be volume times density. And remember that the density of water, if you ever needed in a calculation such as this, 1 gram per milliliter is the value you typically should use. That basically means we have 1 gram per milliliter. We have 150 grams of water, basically. So again, you can use that density value of water, and 1 is pretty much a good value to use. So putting in for our Q of the water in this case is going to be our mass, which is 150 grams. Our specific heat capacity of liquid water, 4.184 joules per gram per degree Celsius. Again, our final temperature in this case, 25.5 minus 23 degrees Celsius. Grams are going to cancel, degrees Celsius is going to cancel, going to leave us joules here. And that's going to give us 150 times 4.184 times 25.5 minus 23. And again, that's going to give me 1,569 joules. In terms of sig figs, again, we got 4 for this one. We got 4 for this one. And technically, when we do this subtraction, that's 2.5, which is 2. Just like I did previously, I'm just going to kind of note where I should probably end up, but I'm not going to use the rounded number at this point because I'm going to use it for the rest of my calculation. Now, for our metal, we could use our specific heat equation. But we do need to use this relationship here to help us out. So we do know that Q of our metal will equal minus Q of our water. So it is an endothermic process here for our water. That means the Q of the metal will be negative 1569 joules. Again, going to be exothermic. The number will be the same, but for our metal, it's releasing it, and that's denoted by the negative value. Now, with that number that we have got from the water, we have the Q of the metal, we have the change in temperature of the metal, and we have the mass of the metal. So once again, dividing these guys to the other side will give us that the specific heat capacity equals Q of the metal divided by the M and delta T. Taking our negative 1569 joules divided by our mass of the metal, 110 grams. Once again, we want to go final minus initial because the metal is releasing that energy. What we see with the metal is temperature decreases. So its final temperature is less than what it started with. So that would get us 25.5 minus 55.5 degrees Celsius. And once again, this here is going to give us a negative number that's going to help us out with the negative number there. And we will end up with perhaps a number. So we'll do minus 1569. Come here. 1569 divided by 110 divided by our 25.5 minus 55.5. Gonna get us a 0.48. Once again, here the units are not going to cancel, so it'll be joules per gram per degree Celsius. Once again, in terms of significant figures, I know really this number up on top should be 2 significant figures. This number is 4 significant figures. And I believe when we subtract this, we get 30.0, which is 3 significant figures. So again, we should end up at 2 significant figures when it's all said and done. Any questions all about there? Questions on specific heat. So specific heat, a super easy way in lab to do an experiment to figure out how much energy or heat in a reaction is basically occurring. Talk a little bit about energy and nutrition. We might have touched upon it earlier. And remember, there's another type of calorie, which is a nutritional calorie, which is a capital C. And one of those nutritional calories is equal to 1,000 of the little calories with a little c, and that's equal to 1 kilocalorie. Now, a calorimeter is a device that is used to measure, for example, the calories in food. It's sometimes referred to something like this as a bomb calorimeter because it's basically a well-insulated device that has water basically in it. And you have something like your cookie there and some wires and some oxygen, and you ignite it. And when you ignite it, obviously here your food product's going to start to catch on fire. It's going to release energy into the surrounding water, which is isolated from the surroundings. And basically your thermometer, you can follow the change in the temperature and very simply just use the equation like we did here. And you basically could figure out how much energy was absorbed by the water, and that energy had to come from, for example, the piece of food that you're burning or whatever you're burning in there. And then you could relate it back to figure out how much energy was lost by the food. And you could change that from a kind of normal calorie, if you will, to a nutritional calorie and figure out how much calories were in that food that was released. Now, when we talk about food and sort of calories, there is what is sometimes referred to as a caloric value for food. And if you look at any type of label, you'll typically see 3 things listed. You'll see carbs, fats, and proteins. And they'll tell you how many grams of each of those are on in that piece of food that you have when you look at the nutritional label. And each of those have a caloric value. And basically the caloric value for fats, carbohydrates, and protein is carbohydrates and protein are 4 kilocalories per gram. And fat is, as you can see in that table there, 9 kilocalories per gram. So basically, if you know the grams of each of those, like you have, say, on a nutritional label, you can multiply them each by the grams of each of them. And basically, that will give you how many kilocalories there are in that piece of food, for example, made up of carbs, protein, and fat. You can then just add them together, and that'll give you the total kilocalories or nutritional calories